I guess I should start. So let me remind you where we are. So in day one, I told you about one of the main problems that we have, which is to count locally as many irreducible characters of a finite group G, and locally, I mean locally means, as I said, related to P subgroups, centralizer of P subgroups, normalizer of P subgroups, intersections of those, etc. Okay, so this is local. And also I defined a very special kind of characters, which are called defect zero characters, which are rare. I mean, they do not always appear. And they are called P defect zero characters, and the definition is one character has P defect zero if the P part of G, you know that the character degree is divided the order of the group, so if the P part is as large as possible. And Richard Brouwer was very much interested in those, and he asked, how many characters can you characterize how many characters have P defect zero group theoretically? And the answer was given by Jeff Robinson. I also tried to convince you that these guys are not local. Again, with commas. Okay, so this was day one. And also something else that I'm going to use today is that, well, they satisfy many properties, these rare characters. And also this property that I'm going to use, that I already told you, is that if chi is an irreducible character, P defect zero, then OP of G should be 1, that there are no normal subgroups of G of order a prime power. So there doesn't exist normal subgroup of G of order a prime power. Okay, so this was day one. In day two, I did more things. And I think that I started by telling you the perfect conjecture, which is the Mackay conjecture, in the sense that this is the Mackay conjecture. That asserts that the number of characters of P prime degree, the opposite of the defect zero characters, you can count them locally in a very nice, amazing way. You just go to one single local subgroup, namely the Zillow normalizer. Okay, then I digressed. This was in the 1971, I think. And in 1986, Alperin formulated his Alperin-Wade conjecture, which seems not related to this one. It's very, very different. And it says that the number of P-regular classes, so this is the number of conjugacy classes of G of elements of order not divisible by P. This was this strange sum. So you take all the P subgroups. Remember that I'm taking all the P subgroups not representative, so I always have this correction of the number of defect zero characters of the normalizer of Q over Q. This received a lot of attention, and it was unrelated to the Mackay conjecture. People, I think, forgot a little bit about the Mackay conjecture and concentrated on Alperin-Wade conjecture. Okay. I also defined, I gave a formal definition. I mean, I was interested the other day in functions. Well, this is the set of functions. This is the collection of all finite groups in such a way that if you have two isomorphic groups, then they have the same value. And in fact, I'm interested in here. I mean, this is a good example, but here you can allow a billion groups, etc. So, okay, so I have this a billion group of functions, and then I defined a new function. If given f a function, I defined f star to be this function. F star of a group is the sum. Before that, I defined chains, but I'm not going to do it again. So this was chains my correcting factor, and f of g of c. So I remind you a little bit what chains were. So C is simply a chain. These are P subgroups. The length of the chain is n. So this is changing the sign. And the stabilizer of the chain, it's simply the, well, I mean, g acts by conjugations of the chain, so it's just the normalizer, the intersection of the normalizers. And I proved something about this f star, which is like this thing. I proved that f star is 0, so I proved. We proved that f star of g is 0 if OP of g is bigger than 1. So this f star have this property. So now notice that f star star equals f star. This is silly, but it's true in the sense that what is f star star? Well, f star star of a group G has this formula of chains -1, my correcting factor, and now I have to put f star, right? Because I'm doing the star of the star. But as I told you before, we proved that whenever you are evaluating in a group that has a normal P subgroup, the result is 0. But what is GC? GC is the normalizer of a chain, so it's the normalizer of P0 intersected with, well, normalizer of P1 intersected whatever. So P1 is definitely normal in the normalizer. So if this is not 1, then this guy is 0. Right? We prove that f star of groups are 0 whenever they have a normal P subgroup. These groups have a normal P subgroup, so f star of them is 0. So everything cancels except the trivial chain when C is just 1. And in this case, it's just, well, the stabilizer of 1 is G, so this is just f star of G. F star of GC, which is G. Okay, just an observation. And my definition, this is a formal definition. Now, I say that f is local if f star is 0. So now, using these elementary arguments, notice that if you have any function, you can write the usual trick as f minus f star plus f star. And notice that because the double star is the same thing, this is a local function. So you can write functions as local. This is to see that is a direct sum plus f star. And f star is very easy to see that it's the functions such that f of g is 0 whenever OP of g is bigger than 1. All this is really elementary, as we have proved everything. Okay. So Alperin announced his weight conjecture, and then Knorr and Robinson came into play, and they proved. So this is a theorem of Knorr and Robinson. They proved that AWC is true if and only if L star equals K naught. We proved this theorem. This was easy. Was playing with chains. But notice now that this is the same as saying K naught is a function here. K naught is a function that is 0 whenever OP of G is bigger than 1. So this means that K naught is the same as K naught 0. Right? I mean, we proved that. Whenever you have a function that is 0, whenever OP of the groups are bigger than 1, then equals the same function. So this happens if and only if L minus K naught star equals 0, if and only if, by my official definition, L minus K naught is a local function. So now Alperin weight conjecture simply says that the function L minus K naught is local. But now I have a little bit of a problem, because what is L? Remember, L is the number of conjugacy classes of elements which are of order not divisible by p. K naught is the number of defect 0 characters. So I'm like adding, how do you say this in English? Exactly, thank you. I'm adding apples and oranges. So what's going on here? Well, let me rephrase. To rephrase, first of all, remember I said this, that L is the number of F irreducible representations of G, where F is any field of characteristic P algebraically closed. I like always to take my little ring, which is very easy. R is the algebraic integers, and M is a maximal ideal containing R. Rada is working with much more sophisticated rings, but she has to pay the price. I mean, if you give Rada's rings to the students, you have to spend like some lectures doing a little bit of ring theory. This is just, well, and with this ring you can work a lot, but you are not as precise as Rada is. You cannot do vertices, you cannot do some stuff, but Brauer characters and much of the representative theory, you can do it with this ring. Okay, so now I need K naught. So what is K naught? Well, so L is irreducible characters in characteristic P, and K naught is P defect 0 characters in characteristic 0. So these are characters, but there is something that I have to tell you, which is the following, and this requires a little bit of algebraic number theory, but okay, I'm gonna say it the way I think you should say it. Should be said. So if G is a finite group in general, and chi is an irreducible character, not of defect 0. If chi is an irreducible character, then, I mean, it would be, remember that you have this nice ring and this nice field, and you have this nice homomorphism, ring homomorphism. It would be nice to put, I mean, you know that chi comes from a representation in such a way that the trace is your character. It would be nice to put here an R so that I can star the entries. And then from every character, you will have an F representation. And this is exactly what is, not exactly, but this is more or less what is happening, but you have to do some number theory, which is the following. Is not, you need to enlarge the ring R. So what you need to do is you define a bigger ring, so I call it S, which is simply alpha divided by beta, such that alpha belongs to R and beta belongs to R minus M. So I localize this ring, and then you also have the map S to F, and then it's a theorem that uses a little bit of algebraic number theory that you can, given a character, I mean, the complex numbers are just way too big, so there exists some representation in S. So there is always a representation in S that affords your irreducible character. And now you can start. Now you can start your representation by starting all the entries. So suddenly, a character, a complex character, then defines, and you can check that everything is well defined, an F representation. An F representation. An F representation, for those of you that, well, you can write an F representation is not a direct sum of irreducible representation because this field is not the characteristic devices of the group. But anyway, you can do it in an upper block triangular, and then, well, in the end, you can associate to every character, you can associate some numbers, which are called the decomposition numbers, and some. These are how many times this representation, I mean F representation appears in this matrix. Okay, to end this story, what I'm trying to say, and I think it was worth it to say it, is that if chi has p defect 0 character, has p defect 0, then this representation is irreducible. This is very rare. P defect 0 characters are very rare, but they satisfy wonderful properties, like this one. In general, when you have a character and you decompose, you go modulo F, you have a bunch of F representations. But defect 0 characters, they are not the unique one, but they are such that X star is irreducible. So now this is not oranges, you said, apples and oranges. Now is the number of F irreducible representations which do not come from defect 0 characters. So this number is local. So now we have that L minus K naught has another meaning. Well, has the meaning, well, as I said, I'm gonna write it down, is the number of F irreducible representations. And rather you asked me if I had a conjecture for today. I do have another conjecture for today. Okay, which are those representations? I mean, the easiest way is to say that these are the representations. I didn't introduce it, but let me allow this. They are, I mean, whenever you have this, a p defect 0 character, and you start it, you have an F representation, and the degree is the same. So in particular, the p part is the p part. But the converse is not true. I mean, there are examples. J1 is an example in which J1 for p equals 2 is an example of a Brauer character which has this equation. I mean, the two part is exactly the same as the two part of the group, but doesn't come from an irreducible character of defect 0. Well, says that it's phi. My conjecture is that for p odd, this perhaps is, well, not a conjecture, a question. For p odd, I haven't found counterexamples. For solvable groups, it's okay, of course.
Finish your equation. L minus
oh, sorry.
mod is equal to the F irreducible.
Yeah, but I wanted to say, for instance, when I was preparing this lecture, I wanted to say minus the number of irreducible Brauer characters whose p part is the p part of the group, but it is false.
But for p odd, you conjecture that.
Perhaps, perhaps. But what I'm going to say here is I'm going to say it fancy. The number of F irreducible representations which are projective. whatever that means. This means that coming from defect zero characters, they are projective. I don't want to go into that because, well, it's just that the big phi for those who know decomposition numbers is just an irreducible character. Okay, and now it comes something which is amazing. I mean, Knorr and Robinson did this inversion formula. By the way, I'm doing everything without blocks. I'm avoiding blocks all the time. With blocks, it's slightly more complicated. I'm doing no blocks. And what they did, aside of doing this inversion formula, that if you put blocks is more complicated than because what I did was few lines. Okay, so they proved the following theorem. This is a theorem, this is not a conjecture. They proved that the function k minus L, number of conjugacy classes minus number of p regular classes, so this is the number of p singular classes, this function is local. Local in my sense, right? Local without local. Let me explain a little bit. Is this deep? Is this complicated? Well, for blocks, it takes a little while. I mean, they use some machinery, green stuff, etc. If you remove blocks, then this is not very difficult, but it's not a triviality. And Marty just gave these days a proof of this in a one page of group theory. Okay, why? What I'm trying to say here is that what is the idea? Why k minus L is local? Here's the idea. If you know a little bit of group theory, you know how to count the number of conjugacy classes of G in a nice way. I mean, if you have an element of a group, you can write it as the p part times the p prime part. I hope that everybody is familiar with this. P part times the p prime part. And then you can count the number of conjugacy classes in a nice way. So you take p elements, conjugacy classes, G conjugacy classes of p elements. And then, so you fix the p elements, and then you need p regular elements that commute with your p elements. So this is L of the centralizer of X. This is elementary group theory. So now, what is k minus L? So if you put here X can be 1, of course. So if you put when X equals 1, you put L of G in the other side. So it's saying that kg minus L of G is xp element of L of the centralizer of X. So using this formula from elementary group theory, you know that k minus L is local. Local means that it can be computed in the centralizers of p subgroups, etc. But my understanding right now of this situation is that local implies local, right? Without the commas. Okay, so this is a theorem, so this is not a conjecture because we're talking about so many conjectures, but suddenly there is something that is still, that we have to discuss because still it's amazing, which is the following. Remember that AWC, the Alpern-Wave conjecture, was saying that, that L minus K naught is local. But now we know by Knorr-Robinson, we know, not a conjecture, that K minus L is local. So one function is local if and only if you add another local. So this means that K minus K naught, if and only if, is local. So the Brouwer characters have disappeared. So Alpern-Wave conjecture, it says that the number of conjugacy classes or irreducible characters minus the number of defect zero characters is local, and it's equivalent. This is I'm not certain. I'm not sure that I do understand this, in the sense that, for instance, I worked with Dieppe in the reduction of the Alperen-Wade conjecture. And the Alperen-Wade conjecture, if you go deep, you don't need L is a number of irregular classes, but you really want to play with irreducible representations. So in the end, what we wanted is irreducible representations of G. And you wanted to go, I mean, we defined something like the vertex, which is not, and we wanted to go to weights, which are also, in this case, they are vertices, whatever that is. So I mean, in the end, if you want to prove the Alperen-Wade conjecture, you want bijections like this. I mean, I'm not defining what is this, but in the end, you want bijections like this. So we published a paper in which we made a reduction, and later Britta did the block version. There is people working on this, etc. But in order to do that, you need to know the Brauer characters. And for some groups, this is still not known. The monster p equals 2 or many Brauer characters, they are not known. So if you go to Alperen-Wade conjecture in this way, you need to know Brauer characters. But suddenly, if you go to the Alperen-Wade conjecture with chains, you forget about Brauer characters. You go to ordinary characters, which are far better, more understood. So what is this meaning? So chains, no Brauer character? I really don't know. I mean, I still have to think on this. I don't know why the L really disappears from the picture. Okay, so now is the time for Dade's conjecture. Okay, I'm going to formulate Dade's conjecture in a clean way, in the sense that, well, Dade's also was very clean, but he did it for blocks. He never formulated without blocks. So I figured it out the way to do it without blocks. And I mean, he did it in 1990 and right here. Not in this place was not built, but some other place over there, or over there. So Dade's conjecture. So finally, Dade's conjecture. Well, if you see Dade's conjecture, you will say, I mean, what is k minus k naught? Well, k minus k naught is the number of irreducible characters which have not defect 0. So you can write this as the sum d bigger than 0 of kd. This counts the number. I mean, every character has a defect. So it's just to say that, well, I mean, this is silly. So what Dade conjecture, in the way that I'm presenting today without blocks, is that kd is local. And of course, I don't have to prove. I mean, he announced this in his Invenciones paper, that his conjecture implied, I mean, not a big deal, but he proved that his conjecture implied Alperen-Wade conjecture, which is clear, right? Because if every kd is local, the sum of locals is local, so k minus k naught is local. Okay, I wanted to show you an example. Okay, so example. S5, if I don't have my computer, it has to be very, so S5. And correct me if I am wrong, but so you start doing chains, computing all the chains. As I said, you can do all the chains to many, or normal chains to many. Elementary abelian chains are probably the best. Also, the so-called p-radical chains are also very good. And this is also where the topologists think that they might have a say in all this, because, I mean, all this, how do you say it? They are homotopy equivalent. So perhaps there's some topology here, absolutely. Okay, so you do all the chains, and in the end, I mean, you think that there are many chains, but in the end, most of them cancel. And when you do S5, I did it with a computer, of course, and then you have that there is only one S4. You have a D12. Excuse me?
What prime?
Oh, sorry. Always 2. And you have a C2 cross C2 with a minus. So in the end, there are only 3 normalizers. All the others cancel. Okay, what are the... So all this story is that if you know the right-hand side, you know something about the left-hand side. And if you think about it, it is pretty amazing. All these are silly little groups. And S5 just, I mean, it's another thing. Okay, so the sign, yeah, I mean, you have calculated many chains. So you have 32 chains in which you have an S4 and the normalizer. Look, all these groups have a P subgroup in such a way that they are the normalizers. So you calculate the chains, and you have 32 S4s minus 31 S4s. So in the end, you have 1 S4. So every chain comes with a plus or a minus. So in the end, you have a bunch of things. So you counted how many, and then the result is 2, minus 2, 3, 4, 5, etc. So in this case, there is only, there could be a 2 here, but in this case, there is only 1 S4. Is this clear? So, okay, so you calculate all the chains, and then you have many, okay, so you have your S5, and you calculate all possible chains, and then you calculate the normalizers of the chains. And these normalizers come, I mean, for instance, this is a minus, this is a plus, etc. So GC is at D8 plus D8, oh, they cancel. So in the end, you just have like, I mean, some groups with a coefficient which can be positive or negative. Okay, there is a authentic book that I'm studying these days, which is related to this, but I don't want to go into that. Okay, so now, characters of S4, I hope I have them right, is 1, 1, 3, no, 1, 1, 2, 3, 3. Characters of D12, 1, 1, 1, 1, 2, 2. Characters of C2 cross C2, 4 ones. Everybody bears with me? Everybody is with me, right? And now, I'm going to calculate Date's conjecture, for instance, D equals 1. Okay, characters of C2 cross C2 of defect 1. What is defect 1? I mean, here the CILO is 2 to the 4. Defect 1, in this case, is calculating characters whose 2 part is 2. That is defect. Defect is not the P part, but the opposite. So characters whose 2 part is 2, this is 0. Here, again, you have that the 2 part is 4 in D12. So again, for D equals 1, you want to count how many characters you have of defect 1, which are whose P part is 2, which is 1 and 2. Now you go to S4. S4 has the 2 part is 8. So now defect 1 means character whose 2 part is 4. There are none. So now what Date's conjecture tells me is that in S5 you're going to have 0 plus 2 minus 0 characters of defect 1. So it's a 2. So what are the characters of S5? It's 1, 1, 4, 4, 5, 5, and 6. The CILO 2 is also 2 to the 2 cube. So we are counting defect 1. So this means that we are counting characters whose 2 part is 4, and there are 2 of them. So this is 0, this one. So check. Now you do D equals 2. Okay, characters of defect 2, now we go faster. All of them have defect 2, so there are 4. Characters of defect 2, there are 4. Characters of defect 2, now the size of the CILO 2 has changed. So defect 2 means that the 2 part is 1, so this is a 1. So the answer should be 1 plus 4 minus 4. So 1 plus 4 minus 4 is a 1. So there should be in S5 an irreducible character whose 2 part is 2, exactly. And this is the 6. And now we go for D equals 3. Of course, when the D is bigger than the order of the group, you get a big 0 here. Now, for D equals 3, the same, 0. For D equals 3, its counting is exactly the size of the silo, so you're counting p prime degrees, 2 prime degrees. So there are 1, 1, 3, 3, there are 4. So it says that 4 plus 0 minus 0 is the number of p prime degrees in S5. And of course, this is 1, 1, 5, and 5. Okay, you do this in every group, and it should be okay. This is what dates conjectures. Okay, now a little bit of history. I have it, I wrote it, I made a Date started with his ordinary conjecture for blocks. What you have seen this, but the block version, which is a little bit more sophisticated, but nothing more. The next step that he did, he published another paper, a very long paper, perhaps 100 papers, in which he did the projective version of his conjecture, in which he proved that this projective version implied the Mackay conjecture, the Alperi-Mackay conjecture. He always was talking about blocks. I will show you in a few minutes how to derive Mackay conjecture for the date conjecture that I stated today, okay, without, an easy way. After that, he announced the invariant conjecture. Then, what is the name? Then he announced the inductive conjecture, the extended conjecture, and finally the inductive conjecture. And he wrote, with a great amount of work, it can be shown to hold for all finite groups if it holds whenever G is an non-abelian finite simple group. So what he was doing was to refine this conjecture in a series of increasingly more complex and complex conjectures in such a way that in the end, if you check that for simple groups, all the conjectures were going to be true. In particular, Alperi-Mackay. In particular, the Alperi-Wien conjecture, because he proved that Alperi-Wien conjecture was a consequence of his conjecture. Nevertheless, it's not my job to judge anything, but this reduction never appeared. I think that it was getting more complicated, or he lost interest, whatever. I don't know. So the final reduction, before I forget, this was 1990, and he was working during the 90s on these conjectures. And finally, the reduction of date to simple groups was conducted by Britta Speth, and this appeared in the GEMS in 2017, perhaps, so very recent. The status, perhaps I should leave this for the end, but in case I forget, I think that now that all the efforts have to go to the Mackay conjecture, because it's the easiest one. This is, you cannot, well, unless you find something wonderful, but in theory, date implies everything, so perhaps it's more complicated. Well, it should be more complicated. So Mackay, now we have the p equals 2, so I should go for Mackay p odd. Okay, now let me show you how date's conjecture implies the Mackay conjecture with a very elementary argument that I found. I need, so this is this argument. So it's a little lemma in which there is only a bit of group theory. It looks a little technical, but you will see that it's not. And it says the following: suppose that f is any of these functions that I'm working these days. Then remember that f star has a complicated f star. You know that there are sums, there are chains, there are minuses, there are stabilizers. So I'm going to write f star as a sum of differences, you'll see it. It's just easier to write. So suppose that P is a Sylow P subgroup. So I'm going to then F star of any group G equals F of G minus F of the normalizer of G of P. So this is a difference of G and the Sylow normalizer. And the same for some chains. I'm going to define these chains right now. Where QD is a Sylow P subgroup of GD. So look at this formula, and it's an easy formula. So it's about differences of G and a Sylow normalizer, of a group and the Sylow normalizer. So what is B? B is simply non-trivial chains C such that the last term Pn of C is not a Sylow P of GC, of the stabilizer. I know it sounds technical. With chains, in the end, things are technical. But if you believe that, and we will just give, I will give a sketch of the proof, then this formula you can apply it, and then you even forget what is B. So B are some chains in which the last term is not a Sylow. You will see immediately how this is nice and how this appears in the formula. I'm going to require a fact, so the proof. I'm going to sketch the proof. And the only thing that I need is one of these little things that you give to your students in group theory class, is that if you have that Q is a P group, P subgroup, then Q is a Sylow of G, if and only if Q is a Sylow of the normalizer in G of Q. With this, we can prove this. Okay? I ask you for a little bit for 3 minutes of your patience. So how can we prove that? Okay, so it's very easy. Okay, let me write. Okay, you ready? I'm going to prove it. So my plan was to prove it, so I hope it's okay. Okay, so elementary group theory. So I'm going to call A to be non-trivial. Please put here normal chains. I always work with normal chains. So I'm going to be, A is going to be normal chains of length n bigger than or equal to 2, the opposite, such that the last term is a Sylow P subgroup of GC. Okay, so I consider the normal chains. I mean, there is here the n bigger than 2 that I will explain later, but okay, so this is easy. Normal chains in which the last term is a Sylow of the normalizer, and those which are not. And the only thing that you have to see, the only trick, is that I can construct a map from A to B. How do you do that? Okay, I have a normal chain. 1 equals P1, Pn. These are normal chains, which means that everything is normal in wherever you want. And I know that Pn is a Sylow of the stabilizer of the chain. And I want to go to B. How do I go to B? Any ideas? I want a chain in which the last term is not the Sylow. So the obvious choice is just to cut Pn. Okay, so I cut P, and I'm going to call it C star. And the only trick, besides this trick, is that what is the relation between the stabilizers? So stay with me. It's just very easy. What is GC? What is the stabilizer of the chain? Well, the stabilizer of the chain is to the intersection of all the normalizers. But you can put first the intersection of the first and then the last one. So this is the GC star intersected the last one. You with me? But now, this is the normalizer in GC star of Pn. Right? So what is the relationship between these chains? The relation between these chains, I have G, the stabilizer, C star, and here I have the stabilizer in C, and I have that Pn, remember that Pn is a silo in this thing. So because Pn is a silo in this group, by the little elementary group theoretical fact, Pn is a silo in GC star. So certainly Pn minus 1 cannot be a silo, right? Because Pn is a silo. Remember that we are looking at chains in such a way that we are looking at chains and we see the last term and we are wondering whether or not the last term is a silo of the stabilizer of the chain or not. We start with one that it is, we cut the last term, and because Pn is also a silo of the big one, Pn minus 1 cannot be one. Pn minus 1 cannot be a silo. Okay, so this is well defined. But just a little bit more. Is it surjective? And how do you construct all the guys here that go to this chain? How do you do that? The only thing you have to do is to add a silo of GC star, right? So how many chains are there? So now you go. So from how many, if you fixed, you have this map, and if you fix C star, what are the chains that go to C star? Okay, I mean, C star is to cut, to delete the last one. So the first n minus 1 have to be the same. So these are chains that look like exactly P1, P2, Pn minus 1. All these are P1, P2, Pn minus 1. And then you have to add what? What you have to add is a silo. You have to add a silo, Q1, Qt, where Qi is a silo P subgroup of GC star. How many silos do you have? Well, the index of the silo, which is this thing. How many silos? This is the normalizer. So this is exactly this number. I mean, if you hear this for the first time, I also would be confused, but this is group theory at the very elementary level. So you just make sure that everything is right. And when you do the counting, when you do F star of G, remember that I'm going to write the definition again. So this was chains minus 1C GCG F of GC, and then you just have to be clever. So you start first with the chain which is 1, which is the chain equals 1, which means that this is just F of G. Now let me count chains which have two terms, chains which have two terms, chains with two terms in which Q is a silo of the normalizer. I have to count that. Chains of two, in which Q is a CILO of the normalizer. Oh, these are Q is a CILO of the normalizer if and only if Q is a CILO of G. So how many? So I'm just counting CILO subgroups. And because I always have this factor correcting, this is minus F of the normalizer of P. Now you do the trick. You start running on chains in B, and you start running on chains in B with those QI. And you just, because you have this number here, cancels very nicely with a number here, and in the end you get what you want. Okay, now I'm not going to waste more time with this because it's just noticing that the coefficients cancel and that everything is okay. I want to go to the last part. So there is nothing hidden here, everything is very easy. So let me finish. So theorem. Dates conjecture. Implies the Mackay conjecture. And here is the proof. The first part of the proof, which I'm not going to do, I did it in my summer school, like in July 2016. So if you were here, there in the slides there. And it's very, very, very nice. And elementary character theory. It's Clifford theory, basically. And the first step is that in a minimal counterexample to the Mackay conjecture, you may always assume that OP of G is 1. Nice character theory. So you assume that it's 1, and then you have a character of P prime degree. You restrict to a normal P subgroup. It has to be a linear character because it's below a P prime degree. And then you show that it extends to the stabilizer. You apply something called Gallagher. You apply induction. Everything is fine. So this is a nice elementary character theory. So now I'm going to use Dates conjecture. I have a variety of KDs to use. Okay, so I have a group G. Well, I have to fix my group G, for which I want to prove that the Mackay conjecture is true. And suppose that the P part is P to the A. So by Dates conjecture, we know, by Dates, we know that the function Ka is local. 1 second, you might think, oh, you are only using Ka, where A is the largest power of P dividing the order of the group. No, I'm using induction. I mean, here I have used induction, so I'm doing the proof by induction. Okay, so I know that K is local. So K is local means that I'm going to apply this lemma. Local means that the star is 0. So this means that the star is 0. But the star with this lemma is F. I apply this lemma to F equals Ka. And I have that this is Ka of G minus Ka of the normalizer in G of P, plus a bunch of things that I don't want even to think about them, which is some change wherever, but the nice thing is that, well, my factor, my correction, and then it's Ka of a group minus Ka of the normalizer of a CILO. Because OP of G is 1, these groups here, these are normalizers of chains, then they are proper. Right? Because otherwise, we will have normal P subgroups, and we know that OP of G is 1. And K of a group can only be two things. Because the p part of p is p to the a, which is the largest one. Here, the a perhaps exceeds the size of the CLOP subgroup, and in this case is 0. I mean, if you have if your a is too big, there are no characters there. Or it's exactly your a, and in this case, it's the number of p prime character degrees. And now you have it. By induction, this equals this. Sometimes it's 0, and sometimes it's induction, Mackay conjecture. And then you arrive to this number. This is the number of p prime characteristics of G minus the number of p prime degrees of the normalizer of P. So Date's ordinary conjecture does imply the Mackay conjecture. Just 2 minutes. Where to go from here? I mean, I haven't said all the refinements that we have been finding in these years, but if you put everything together, for instance, Isaacs and I, we found that there should be bijections in such a way that the degrees coincide for the Mackay plus or minus modulo p, so this sort of hints for isometries. Brouwer's conjecture also predicts isometries. If you attended Carolina's and Bandy's talk last week, there is also some Galois action that is non-trivial, and it's giving a lot of information. And all this is hinting that we should work over the p-adics, in this case, p-adics. Now you have seen homotopy theory, so homotopy. Of course, blocks. I mean, I have been avoiding blocks all the time. Blocks are algebras, so perhaps there is something about algebras that we are missing, so blocks mean algebras. So there should be a way, if there is a proof, without using the classification, there should be a way to put all this together, and we are waiting for the right person to prove this. And I will stop here.
So just to clarify, so what your theorem is really saying is the usual thing that a minimal counterexample to Date's conjecture is a minimal counterexample to okay.
Yes.
So it's not group by.
No, you're assuming that you're doing induction, so you're assuming that this conjecture is true for every group of a smaller order, and then both are equivalent. Yes. Yes.
A lot of what you've written just, I don't know, feels kind of homological.
Yes.
Me, and you mentioned you're talking about you're thinking about some K theory. Is there anything more you can say about it?
I have not. I didn't go deep into that, but I advise you to go to a paper by Jack Tevena, in which he reformulated Alpern-Way conjecture, not Dates, in terms of K theory. And also there is reformulation by Linkelman about Brendan cohomology. I mean, there are many different formulations. It seems that AWC is very deep in the sense that it has many connections with several parts of. And there are more equivalent formulations. Perhaps I'm forgetting some, but yes, for K theory, the Tevenat paper, you have the reformulation of Alpern-Way conjecture.
In terms of equivariant topological K theory, not algebraic K theory.
Oh.
But yeah, but it's still.
Okay, I thought it was the.
It is K theory.
Yeah, it is K theory, yeah.